is going to be more expensive than just link-by-link recovery. So it's a trade-off. You will eventually recover, but that's a trade-off. If you're using links, losing a lot of packets, you might be better off recovering right here, putting in some extra work, even though it means that the functionality is duplicated. But if you rarely lose packets, then you say, well, you know, it's a rare event, and if it does happen, TCP will take care of it, so I'm not going to worry about it. Okay? Any questions? Okay. So move on. Some of the other things I'm just going to run through that the link layer may or may not do, depending on the specific link layer protocol we talk about. Flow control, spacing, sending, and receiving nodes so that buffers don't fill up. Error detection, there's all kind of reasons for errors, and again, how you do it, how aggressively you do error detection and error correction depends on your link type. And you can have half duplex and full duplex within link layer. It's just basically really terminology. With half duplex, nodes at the both ends can transmit, but not at the same time. So half duplex means that if A and B are there, either A is talking to B or B is talking to A, not both of them at the same time. And full duplex simply means that both of them can be simultaneously having a two-way conversation. Okay, so we'll come to all of those as we go along. So one more thing about link layer that is new is that link layer is almost entirely implemented at the adapter level. Okay, it's not, the link layer processing does not happen inside the computer. So we saw that TCP, UDP, even routing tables, all those are the user level processes running as regular processes under the operating system. But the link layer is running on your Ethernet card or PCMCIA card. The generic name for adapter is NIC, Network Interface Card, I guess. Right. So again, these are the services that we talked about: encapsulation, error checking, flow control, etc. All of them are done at the NIC or the adapter. So adapter is so semi-autonomous. So yes, it's connected to your computer, and eventually the traffic goes and comes from your sending computer, but the all low-level processing is independent and does not load your CPU, and so it's most of it, a lot of it is in the hardware of your network card. Okay. Any questions? So link layer is fairly close to physical layer. So we do not talk too much about physical layer in this class, but everything that the link layer does is very closely related to the physical layer that you're running under. Okay, so first we talk about error detection that is done at link layer in many of the protocols. So instead of being protocol specific at this point, we're just going to see how we do error detection. So the basic idea is very straightforward for all error detection schemes. You have a datagram that comes in, so that's coming from IP layer, comes to the link layer. This is the original datagram, and from the datagram you compute error detection and correction bits. So you put a couple of new bits that are computed from this, from the original data. Everything is sent, the same stuff gets here. You recompute the error detection and correction bits. If you get this is 11011, you recompute and you get 11011, everything is good. If you get anything else, then there is something wrong. All the data is corrupted. Okay, so you have some rules of computing the error correction bits or detection bits from the main data, and those two have to match on both sides. Okay. So the exact rules. So now the question is, how do you compute these bits from the data? And those rules can vary. So let's start with something really simple, which you've already seen. There's something called single bit parity. So all you're saying is you look at data. So of course it's binary data, it's zeros and ones. You count the number of ones, and if the number of ones is even, then you put a 0 here, and if the number of ones is odd, you put a 1 here. Okay. And then when the data reaches the other end, you count again the number of ones and confirm if it's even, then you check, is this 0 here or not? And if it's not, then there's a problem. If it's odd, you check if it's 1 here or not. So you're just checking parity, and it's going to protect against single bit errors. Okay. If you assume that the worst that can happen is that one bit can get flipped, you're fine. However, clearly, if more than one bit gets flipped, if both these ones become zeros by accident, then the parity is not going to help you. Parity will still be the same if 2 bits get flipped. So it's not particularly useful in practice, because it's quite likely that when one bit has a problem, the next one also might have a problem. So this is really for illustration here. Okay. So that's one way. You could try to improve on that and have something called two-dimensional parity. You take your original number, you break it up into multiple rows, and so the original number is just these. Okay. Now you compute parity for each column and each row. Okay. So here's this. So this is from this row, and this is from this column. So this is 1, this is 1, it's even, so it's 0. This is 1, 1, 1. There's 3, 1, so it's odd, it's 1. Okay. And so these are your parity bits. And when you reach the other side, you again check if all the parity bits are still good. Okay. So the key here is that it allows you error correction. Okay. So if you see that this bit is wrong, so it was you're expecting. Let's see. So what happened during this transfer was that this bit got corrupted. Okay. So this bit got corrupted. So you end up getting this this data over here. So you recompute all the parities, and you find that this is okay. You count everything. You count this one. There's 1, 2, 3 ones, but the parity bit says 0. So there's something wrong. Everything is okay here. Everything I think is okay here. You count this way. Everything is okay. Everything is okay. Everything is okay. Over here, you have 0, 0, and 1. There's only 1. It's odd numbers, and it's saying it's 0. So that is incorrect, and this is 1. So what you do is you have this one that is wrong and this one that's wrong. You combine them, and you can figure out that it was exactly this bit that got corrupted. Okay. So again, not necessarily super useful in our context, but you have more overhead. Instead of 1 bit, you have 1, 2, 3, 4, 5, 6, 7 or 8 bits that are parity bits. And the additional power you get is that if 1 bit is flipped, if you assume 1 bit is flipped, you know which one. You don't have to ask for the data again. You can just correct it on the spot. Okay. So any questions so far? Not